Hi, I'm Yuji. I'm a second year PhD student at the Space Rendezvous Lab at Stanford University. Today, I would like to talk my presentation towards robust spacecraft trajectory optimization via transformers. It's a collaborative effort with Stanford Autonomous Space Systems Lab and also like Space Rendezvous Lab under the umbrella of like a CSER, Center for Aerospace Autonomy Research. So, quick motivation and background. The needs of on-orbit servicing or in space like assembly, manufacturing, and in general logistics are upcoming key technology for the space economy, and that those applications always require some sort of like autonomous rendezvous capability. And ideally, we would like to make this autonomous capability also on board so that like spacecraft can decide where to go or like how they navigate around like a particular object. And then particularly in guidance and control algorithms, there are like mainly two streams of philosophy or way to control. One is like a closed form algorithms, which is really nice because of like it usually have like a semi-analytical or analytical solution or like a guaranteed convergence, which is very like ideal for spacecraft operations. However, they're usually tailored or like they have some like scalability issues. Another way of building these like control guidance and control algorithm is like optimization based numerical algorithms. And it has very general form of like optimization and then like leverage a recent advancement of like numerical optimization algorithms. So it has a broad applicability and then it also provides a guarantee of like constraint satisfaction as much as like we model. However, like usually it incurs like a high computational cost, and especially because spacecraft flight-ready GPU, CPU are usually much worse than like the current state of the art on the ground. It requires us to do some modification or some like advancement in terms of onboard deployment. So there is a new paradigm of like learning-based methods are coming in, especially from the robotics community. And then there are like a stark comparison between optimization-based methods and the learning-based methods. Optimization-based method generally guarantee the constraint satisfaction, which is really nice. While, as I mentioned, onboard computation is still a big challenge for the entire community, especially for spacecraft guidance and control. On the other hand, learning-based methods, once trained on ground or offline, it can capture an entire solution space because we can like collect a large data sets before we deploy it. However, the generated trajectory usually doesn't have like any guarantee of like performance or like the constraint satisfaction, which is going to be a very big issue for a safety critical system in general. So there is a big philosophy of like using learning-based method to warm start, namely to build an initial guess to feed the following like non-convex or non-linear optimization to ensure the like guaranteed satisfaction of the constraint. So as shown in this streamline, there's like an offline training that we do, and then once the neural network is trained, there's like we throw in the non-convex or non-linear optimizer on the on board so that like hopefully, for example, in this very complex solution space, the neural network suggests to start the entire iterative algorithm here, but not like somewhere here or here. That will take much longer convergence, and then like they may not even converge to the like where we want to converge the solution. So in the last year or two, we have been proposing the architecture called autonomous rendezvous transformers. And to give a brief introduction of like what autonomous rendezvous transformer or ART is, it's very much inspired by the recent advancement of like large language model or in general sequence modeling, where we tokenize like a specific sentence into like a small pieces of chunks, for example, words, and then by feeding them like step by step, we train the neural network or transformer to predict what is coming next. For example, in this example, we feed like the house is on, and then like transformer predicts or like gives a probability distribution of like what would be the word coming next. And in this case, like there's like a fire or sale that's coming up to the like next candidates. And very similarly, in the discrete time step, we can do the same thing for like the trajectory in general. Essentially, we are trying to build a time series prediction of like a trajectory, which is also called decision transformer. As we feed like states and then like control, at the end of the day, we auto-regressively generates what is coming the next state as well as like control. And then once we did that, we can auto-regressively like or iteratively like do like this process to generate the whole sequence of like states, namely trajectory. And there are a couple like key observations I want to make. In general, guidance problem solves like optimal control problem. And then from the well-known Bellman's principle, optimal control is fundamentally Markovian. However, we have been observing that sequence modeling prediction still helps a lot to generate a high quality trajectory, especially in the learning-based framework. And also, one big advantage of like using transformer for like this architecture is that transformer is fundamentally like supporting like the multimodal inputs. So to generate the trajectory, it has like a very high generality of like input and also like output. So like although we are just talking about state and control, the extension is like much easier to make compared to other methods. So again, like using a bit of math, like the inference pipeline of the art is like shown as here. We feed the boundary conditions and performance parameters, and after we train the model, the transformer generates the initial guess, which is now fed to the like nonlinear or non-convex optimal control problem or optimizer, and then we get the optimal trajectory to deploy. And the past works, there are a couple related works in this art pipeline, in art paradigm, including open loop optimal control or model predictive control, or like recent work also focuses on multimodal inference. However, there are still like key challenges remain towards like a deployment in the like space, which we want some robustness or like fault tolerance. And also another issue like or key challenges we have is we haven't been able to figure out how to basically prevent the so-called hallucination or some like rarely happening catastrophic like output of the like machine learning's output, which is like almost inevitable as long as we are using learning-based method. And those two are still remain, and then like, but which is really critical for like the future deployment in space. So we set the problem statement and the contribution as follows. We are making like the explain the like autonomous rendezvous transformer architecture. And then like we now present like a two major extension, including like the adding addition of like robustness to the uncertainties in the fault tolerant trajectory optimization, which is much more realistic in the like the trajectory optimization scenario that we want to deploy the spacecraft. And also like we introduce what is called post hoc acceptance check, namely after the art or transformer generates the trajectory, we add additional criteria so that like we can distinguish, oh, is this initial guess will be like seems to be good enough to start the following nonlinear optimization. So first of all, I would like to show the overview of like what we want to solve at the end, namely fault tolerant trajectory optimization under uncertainty. So this is formulated as like what is called chance constrained optimal control problem, or CCOCP. And there's like a objective function, arbitrarily objective function you can choose. And then the first constraint is dynamics. And then second constraint defines error covariance and then the state relationship. Since we are the main concern is like open loop control or guidance. We assume to model the uncertainty around the state, we assume there is like a priori model for like the error covariance that is mapped from the current state. And then the third one is very interesting, which is like a path constraint, but shows the probabilistic satisfaction of fault tolerant constraint. And you see the probability operator here, but essentially we would like to ensure the satisfaction of constraints with like, let's say 99.9% or like 3 sigma or something like that, which is sort of realistic assumption considering most uncertainty sources are modeled as like a Gaussian, which is unbounded. So in order to like rewrite this like probabilistic constraint, which is currently infinite dimensional, which is almost impossible to solve, we would like to rewrite this chance constraint as follows. Now you can see the chance constraint is rewritten as a deterministic form of like a mean evaluation, which takes a state. You can see like the n star, and then also you see the beta, which takes a error covariance as a like argument. then this expression is sort of equivalent to like solving the original infinite dimensional chance constraint with just single like finite dimensional constraint. The caveat here is like this incurs non-convex constraint. So like it motivates us to use like a nonlinear optimizer, which includes like sequential convex programming. So the shown figure is like a workflow of art where you start with like a dataset generation where you basically generate a lot of like set of data to like feed the neural network and train. And then after we train, then we move on to the deployment, which includes like inference, essentially generation of an initial guess, and the following like optimization as we discussed. And there's like you see like there's like two phases of like preparation, essentially how we train or make art, and then like the second part, how we deploy art. So we would like to go over the preparation and then like deployment step by step. The first one is like the key component of like art is like a tokenization or the definition of the state representation. Here we define the state trajectory sequence tau as like follows, like a string, like a sentence or a string, as a sequence of like the performance parameter, which I will talk in soon, and also state, and then a control. And then again, performance, state, control, and so on and so on. And here, performance parameter contains like two elements. One is like called reward to go, which effectively tells you like how much cost you want to spend in order to get to the final point. And then also constraint to go, where like how much constraint violation you might want to allow for the spacecraft. In general, this is going to be 0 constraint violation, obviously. And the novelty we added here compared to the previous research is like in order to evaluate constraint to go, as we discussed in the previous slide, we added this like chance constraint term to feed into the like constraint to go evaluation. And because like we converted the infinite dimensional chance constraint to the like finite dimensional equivalent form, we can now explicitly feed this evaluation criteria to like trigger the constraint to go evaluation. And then after we set up this state representation, we now like solve the batch of like chance constraint optimal control. For this case, we use like a sequential convex programming, and then we generate like a lot of data, like shown here. So after we get a lot of trajectory, then like we start training a transformer, as shown here. Essentially, as I mentioned in the inference pipeline, we would like to feed the reward to go, constraint to go, which is a performance parameter, and state. And then like we would like to expect transformer to predict the state. And then after that, the following predict the control, and then also the following state. And then by using like the least square for like these like predicted control, and then like the desired control, as well as a generated state and then desired state, we are able to like train the like art so that like it will predict the like upcoming state and then the upcoming optimal control properly. Okay, now let's move on to the second part, deployment. The deployment like pipeline is shown here. And there are like two like key important features that has like in this like figure. One is like dynamics in the loop inference. When you like have like autoregressive inference of like this like transformer, we leverage is like art's capability to predict the optimal control input, but not their capability to predict the state. This is because in the realistical like guidance scenario, we usually have like a dynamics model like on ourselves. Maybe that's a reduced order model, but we have some like knowledge about the dynamics, so we would like to leverage that in order to have an accurate trajectory generation. So art only generates the control, and then like at each step they propagate the dynamics but for one step, and then like so the like inferred initial guess is always dynamically feasible. And although the initial guess is always dynamically feasible, note that like this will end up to like always like off, the terminal state is always off from the desired terminal state, if that makes sense. And after that, the second like component, the key component is like something we added newly, which is a post hoc acceptance check, where we would like to introduce some like metric like shown in here, where our art indicates like the return, like the the reward of like the generated trajectory, while our desire is like something we originally query. And then similar for like the constraint evaluation, so that like we can check these values to see if their generated trajectory is close to what we actually query. For example, like are they like violating constraint or a law, or like are they like kind of matching the reward that we queried originally? So the scenario like we are solving these problems are low Earth orbit rendezvous, including the fault tolerance scenario. The objective function is like minimization of sum of L2 norm impulsive control in the like radial tangential normal frame. And because like now like we would like to consider some uncertainties, multiple sources of uncertainties are like added in order to model the function of like from the current state to like the state covariance. This includes navigation uncertainty and the actuation uncertainty and unmodeled dynamics. For the confidence level, we incurred 99% satisfaction rate. And another key fault tolerant constraint is like a passive safety, where we would like to enforce the spacecraft to be outside of like what is called keep out zone and approach ellipsoid for both control trajectory, but also drifted trajectory. So like at any single instance of control, when you lose that control authority, the drifted trajectory is like still outside of like the sort to say like the area or domain of interest. We collected like 115 trajectories, like in showing here for both deterministic trajectories and then like the chance constraint trajectories. And then we randomized the initial state as shown, you can see in the right bottom, and then also the terminal states as shown in the 4 waypoints you can see in the red dots. So I would like to briefly show what we want and what is actually happening in like art initialization. This is really great example where if you solve like a convex solution, which only like takes like the boundary condition into account, but not the passive safety, you'll have some like black trajectory, which has like delta V of like 4.792. And then when you use this trajectory to initialize the passively safe sequential complex programming, it will fall into this like blue one, which is pretty close. But you see like the delta V bumps up by like 0.5 meters, which is quite a lot. However, after the training, art infers from the same initial condition, the same terminal condition, art infers something like orange, which has like a lower delta V, which is because actually they are not like satisfying the terminal constraint. However, once you start the sequential complex programming from like yellow part, the converged solution, which is red, is like not only passively safe, but they almost like hits the lower bound of like the delta V. So this is the power of like art. It's very difficult to predict like, oh, there's actually a nice solution here, for example, if you only have like a convex solution. So that is something we want to see, if that makes sense. So we deploy like 3 statistical experiments. One is like the comparison of like chance constrained optimal control and deterministic optimal control. Second one is a comparison with different state representation. We briefly talked the details in the paper, but we actually made 2 models. One is trained based on the relative orbital elements state trajectory, and the other is like a just Cartesian trajectory state in the like RTN frame. And then we compare the performance. And then the final one is like the post-hoc acceptance check. As we introduce a new criteria, are we getting a better results? So first one is like a comparison of like a chance constrained optimal control and deterministic optimal control. There are a lot of like metrics we are comparing here statistically, but especially the one we want to focus is like the one which I like box into the red, which is the infeasibility rate of like the sequential complex programming. And for both like cases, we do see some like outperforming like metric of like art compared to the naive initialization using like the convex programming. However, especially in the chance constraint scenario where we expect higher infeasibility, art still successfully suppresses the infeasibility rate compared to the like naive convex initialization, where like it really suffers from like going to like the convergence from their like initial guess. And then for the sake of time, I would like to skip the comparison with state representation detail, but we also confirmed in the paper that the model trained in the like relative orbital elements frame, relative orbital elements, and also like the Cartesian states almost perform like equivalently, showing that the R or transformer is capable of like learning a different like state representation in general, showing the powerful expressibility. And then finally, after we did like this statistical analysis, we had some like distribution of like a solution of like where it falls in. And then based on the like these criteria that which I put in the right top, we set another post hoc criteria to sort out the solution. And then like we only take the R generated trajectory if these criteria are met. Essentially, like this tells like reward and constraints are close to what we expect initially. And then other than that, we throw out like those like R generated trajectory, and then as a backup solution, we trigger the convex solution and then start the SCP. As a result, when you see this histogram, you see that there are like almost like no cases of like trajectories which which is initialized by art and also like performing worse than the convex initialization. While like in the original formulation, there are some trajectories which shows like a worse performance than the convex initialization, which is like a huge issue for online deployment. So for the conclusion, we extended the autonomous rendezvous transformer framework in two directions. One is like a consideration of chance constraint optimal control problem for stochastic and fault tolerant spacecraft trajectory optimization. And another key part is like introduction of like post hoc acceptance check. Even though the post hoc acceptance criteria we introduce is very simple, it shows like a powerful like tool to like reliably use like such a learning-based method for like the safety critical systems deployment. Future work includes like the runtime analysis on the flight proven GPUs. We are very interested in like seeing how these like inference time changes when we like throw into the like much like low grade GPU, which is like a flight proven one, or we are very interested in like distilling these like neural networks to see the trade-off of the size of the model and then the performance accuracy. So that's it. Thank you so much.